that given E subset of R, E contains an affine, a non-trivial affine copy of S. What does that mean? That means that there exists X in R and T non-zero such that X plus TA is contained inside. Okay. So somehow all pattern recognition or avoidance problems all boil down to some variant of this question. For pattern containment, the answer to there is that such inclusions actually hold, and for avoidance problems, it's E doesn't contain any such affine copy. Okay, so I think we better start with some examples. So when I say that when is it true, I think it's better to say that there are some easy answers. So E has to be large. So this is a very intuitively obvious concept. For example, if A is a 3-point set and consists only of 2 points, then there is no way E can contain any non-trivial affine copy of A. So that, of course, has to be true. But we are going to see today that a lot depends on the exact formulation of largeness, and sets that are large according to some metric may still be able to avoid existence of non-trivial patterns. So let's talk about an example. Let's say A consists of 3 equally spaced points, -1, 0, and 1. So non-trivial affine copies of F are 3-term arithmetic progressions. Okay, so what we are going to do today is we are going to use these arithmetic progressions as our today's goal is to sort of choose this as our pattern. So our pattern for today. And we are going to use this as a prototype to show how to construct large sets that are still able to avoid patterns. Okay, so goal for today is to prove or at least sketch a proof of the following theorem, that there exists a set E, subset of 0, 1, with the Hausdorff dimension of E equal to 1, so full Hausdorff dimension, such that E does not contain any three-term APs. So I'm going to use this like small result to kind of give an example of a bigger meta principle of how to construct such large avoiding sets. By the way, I know that Ashwin has covered Hausdorff dimension in his lectures. So can I get some of the students to tell me what you remember about the concept of a Hausdorff dimension? This is over to you. So whoever wants to go, please unmute
Yeah.
and give us a go.
So let me say this. And so some of the students who are there, actually, these are the first year BSc students. And so
Yes.
they haven't have at least idea. They haven't have any idea about this Hausdorff dimension at all because they haven't seen the measure theory as well.
Okay. Did has
Okay. So,
ha
okay.
it,
1 second, 1 second, 1 second, Malvika. What if the student wants to say something?
yes, please. That's the point.
Hello, ma'am. I just saw Dr. Ashwin's lectures on. I attended his recent talks online, and I
Yes.
think I can give a sort of formal and not so formal idea of Hausdorff dimension. Just a sort of
Yeah.
informal description from what I understood from it.
Yes.
Initially was uh, it is basically a super informal description would be that it's the Goldilocks zone where a certain set is measurable. So
Okay.
uh, it does not have measure 0 or infinite in that
Okay.
particular dimension
Correct.
with the Hausdorff measure h to the power s of that set.
Yes.
So it is a more formal version would be the supremum of all t such that h to the power t, uh,
Yes.
the Hausdorff t measure of that set is infinite, or the
Yes.
infimum such that the Hausdorff t measure of that set is 0.
Thank you. Yeah, that works great. That's both as a informal description and the formal description that does very well. So what I'm going to do is to keep things simple. What I'm going to do is I will remind you perhaps if the description of a Hausdorff dimension seems a little bit too complicated, I'm going to move over to something called the Minkowski dimension, which is much easier to understand, and we'll work with that. So let's say you have, what is a Minkowski dimension? So let's say cover E efficiently. Efficiently meaning that don't if you can get rid of something and still cover it, then get rid of it by intervals of length delta. Okay. And suppose that we need n delta e many such intervals for the cover. Then, an easy way to describe dimension, not the Hausdorff dimension, but the Minkowski dimension, is to say that this is the log of n delta of E divided by log of 1 over delta as delta goes to 0. So this is probably a little bit easier to define, but it tries to capture a similar notion as Hausdorff dimension. So for the moment, I am going to replace it by the Minkowski dimension with the understanding that this is always larger than the Hausdorff dimension, which you just now described, and quite rightly so, as the Goldilocks zone where the set E admits of it kind of moves from having infinite measure to zero measure. But I'm not going to get into all that measure theoretic mumbo jumbo right now. Let's keep things simple. So we'll just talk about the Minkowski dimension being one. Okay, so with that goal in mind, how do we go about? So there are, as I said, this is really, I'm going to use this as a prototype for a more general principle. There are going to be two steps in this construction of an avoiding set. So here are the steps. The first step is number one, to try to borrow some intuition from the integers. So construct a large avoiding set in the integers. And then try to, step two is lift it to the continuum. Okay. All right. So what I'm going to do is show you. So these are very well-known avoiding sets, and it's also beautiful for many reasons. And my hope is to sort of go over this with you so that we can all enjoy this together. So let's go through each step at a time. So this is step one. Step one in for the prototype that we are considering is to find an AP free, a large AP free set in the integers. Okay. So this idea goes back a long way. So due to Salem and Spencer, and this construction that I'm about to show you is due to Berendt. And it goes along the following lines. So the principle that you have to keep in mind is that, and it's not going to make any sense, but I'll try to clarify this. So the principle is that spheres or circles do not contain APs because of their convexity. So this part I know you will believe, because if you draw a circle, because it is strongly convex, if you take any 2 points on the circle and join them, the midpoint, of course, cannot lie on the circle. So this is believable. But how do you take this geometric object and turn this into a subset of the integers? That's the real question. And let's talk about that right now. So the idea of Salem and Spencer and also Berend was the following. Suppose you take a look at this set. So we want to take a subset of the integers, so fix a base, an integer that is 2, 3, or higher. You can fix b to be 2 if you like. Okay. And you define this set A of, so it's going to have two parameters, R and K. We are going to look at the set whose elements are of the form dj b to the j goes from 0 to k minus 1. Okay. The dj's are digits to the base b. If you want to think of this as our standard integers, think of b as 10. Okay, so maybe that's the best way to go about this because this is the way we represent integers. So let's say dj is between 0 to 9. So these are the possible digits. Okay. And how does capital R come into the picture? Well, we will only consider those dj's for which summation dj square is equal to R. So basically, these digits lie on a sphere of radius square root of R. So this is the key piece where this connection with the spheres comes in. Okay. All right. So these are, so I have a few couple of questions for you. I want to say that this is a subset of the integers. What is the largest possible value that this integers can take? So think of our base 10. You are looking at digits. You are looking at integers whose lengths are consist of k many digits. So what is the largest possible value of such integers? Any thoughts? Okay, let's start small. Suppose k equals 1. What's the largest value of dj?
Sorry, just a question. Are we considering this with some given R, or just you want largest?
Right? No, no, no. Right now, I am just asking these numbers over here. How large can these numbers possibly be given a value of k? Right now, R is fixed, and in fact, R is going to play a very important role, and I'm going to come back to that. But right now, it's a very simple question. If for a fixed k, how large can these integers possibly be?
So I mean, if we're not having this condition on summation dj squared, then set each dj to be as high as possible. So each dj is 9.
Yes, exactly. And then if you have it for, let's say, up to a general k, what is the largest possible value then?
If I understood your question correctly, it's 999 k times.
Correct. Exactly. So this would be, in fact, if you just go one step higher, this is contained in Z mod. So if we could do this up to B minus 1, This is contained in Z mod B to the K. In other words, this is contained inside 0, 1 up to capital N minus 1, where capital N is B to the K. This is exactly what you said. Okay, great. So this is the set that I'm going to consider. And as you asked, what can we say about capital R? So I'm going to make two observations. For every R, ARK is AP free because of the whole because the integers lie on a sphere. Okay. And in fact, just so that when I sum them, I don't run into issues of when the digits sort of running over B, what I'm going to do is I'm going to make this a little bit smaller precisely to avoid this. So let's say I put this as B over 3 or B over 2, so that when we add, there are no concerns. Okay. All right. So ARK is AP free. That's number one. And number two, and how many R's can there be? What are the different choices of how many choices of capital R can there be? Over to you. So remember, R obeys this relation. So what is the smallest possible value of R? Well, just to set you off, if all the DJs are the smallest number, for example, 0, so clearly R has to be larger than or equal to 0. What is the largest possible value of R? Say, for example, that it's all the DJs are B over 3. So what is the largest possible value of R in that case?
K minus 1 times B square over, sorry, K times B square over 9.
That's right. K times B squared over 9. Good. All right. So we have that many choices. And finally, let's say we add up all the cardinalities of ARK. Fix a K and add up over all these R's. What shall we get? Remember, let's go back to the definition. We took all the integers between Z mod B to the K, or between 0 to N minus 1, and we kind of classified them into spheres of radius R. So when we add up over all these different radii, what do we get at the very end? What we get is really the cardinality of the sum j from 0 to k minus 1 dj b to the j, where this condition is no longer there, but all the dj's are just in the between 0 to b over 3. Any questions so far about this step? And if not, then you tell me what the cardinality of this set is. These are the possible digits, and there are k such digits, d0 to dk minus 1. So what's the cardinality of this set? Any thoughts?
Okay, so k digits and b by 3 plus 1 choices. So b by 3 plus 1 to the k.
That's right. Thank you. b over 3 to the k. Great. So we have this many choices of R, and the corresponding sets ARK, their sizes sum up to this. So by the pigeonhole principle, there exists an R between 0 and k b squared over n, such that the cardinality of ARK for that R is larger than b over 3 to the k divided by the total number of possible values of R, which is k times b squared over n, b squared over 9. In other words, this is b over 3 to the power of k minus 2 divided by k. Okay. So what have we? This is our set. So this ARK is the set that we are. So this ARK is the large AP free set in Z mod n. Okay, so let's see. Um, Remember, this was our goal for at least for step one. The step one was to find a large AP free set in Z. So for every large enough capital N, and as becomes larger and larger, capital N grows bigger and bigger, this construction of Berendt, Salem, and Spencer gives us a large AP free set inside this, largeness being determined by this lower bound. Any questions so far? Okay. If not, I'm going to move on to step two. So step two is about how do we take this discrete set and lift it to the continuum. So lifting a discrete AP free set to the continuum. All right. So there is a standard way for doing this. And well, I'm not going to say that this is a magic bullet that works every single time, but it works in many instances. So it's good to know what that is. So here is what we are going to do. Let's start with 0, 1. Okay. And we are going to define, let's say this is, so fix a capital N. Okay. And suppose we stick in, um, we break this up into pieces 1 over n, 2 over n, 3 over n, and so on. And what we do is we are only going to, so let A sub n subset of Z mod n be an AP free set. So what we do is we are going to define E1 to be those points A over capital N plus 0 to 1 over n. So just a 1 over n thickening of it, where A belongs to A sub n. Okay. So that means, let's say we have picked some points over here, and these are, sorry, I should have made it smaller. Okay. All right. So these are the points that that have been picked. So these are the ones that belong to, um, let's say A sub capital N. So, and for each one of them, I'm going to consider a thickening of it. What does that mean? So that means that for this, I will add on this set. For this one, I will add on this one and this one. So my final E1 is going to be the union of all of these red intervals. Okay. Now, this is what we are going to iterate from this step forward. So let's continue. So similarly, so iterate this. At the next step, let's write A over n plus 0 to 1 over n, which is the basic interval from the first step. And we are going to break this up into parts. A over n plus b over n square plus 0 to 1 over n square. And we are going to be taking the union of this, b from 0 to n minus 1. And we are only going to choose those b's for which b belongs to A sub n again. So choose E2 to be of the form A over n plus b over n square plus 0 to 1 over n square. And what does this do? This, where A and B are now both in the integer avoiding set A sub n. Okay? So we continue in this fashion, and let's take so my final set E, so the final, these are nested sets, is capital E, which is the intersection of all these ENs, and from 1 to infinity. Notice that E1 contains E2, contains E3, and so on. And the claim is, of course, E is AP free and has Minkowski dimension 1. Okay. So let me see. I'd like your So we have two conditions to check, the AP free condition and the dimension condition. Which one? So do you have any thoughts on either one of them? Because I'd love to hear what they are, and then I'll put this down on paper. Which one seems easier to handle?
So just for AP freeness, what it feels like I would like to do is say that, okay, take 3 points in my set, uh,
Yes.
and then it, look at which, no, they're in all of them. Uh, no, sorry, I was slightly confused.
No, it's okay. So how about we do this one step at a time? So let's ask clearly, here's a question. Um, is E1 AP free? So let's ask a small question and hopefully that will lead us to the bigger answer. So here's a little question. Is the set E1 AP free?
It's not, but it only has sort of small APs in those thickenings.
Very good. So it's not, but if let's say X, Y, and Z are contained in E1, form an AP, what can we say about X, Y, and Z? I think you said the right thing. Do you want to sort of may
Yeah, I think,
formalize that?
yeah, they need to belong to A by n plus 0 to 1 by n for
Yeah,
the same A.
yeah, exactly. So then they fall in the same basic interval. So these ones are called basic intervals of E1. So this is exactly what we are going to show. And this is how, once we show this, the exact same argument will show that at step E2, if XYZ form an AP in E2, then they must lie in the same basic interval, but the basic intervals in E2 have shrunk in length to 1 over n squared. And as you go down the road, if they have to sort of lie in every single basic interval, their separation is at most 1 over capital N to the power of some little n, but that little n goes to infinity, ultimately making x, y, and z all equal. So this is really the way we need to go, that each step takes us a little bit closer to becoming AP free. But it doesn't quite get there at any finite stage, but it gets there in the limit. So what we will show, so suppose, so I'm going to take that statement up there, this one, and prove that over here. Okay. So suppose X, Y, Z belong to E1, which means that X is sum A sub X over N plus delta sub X. Y is similar. It's A sub Y over N plus delta sub X, delta sub Y. And similarly for Z, and these A sub X, A sub Y, A sub Z, these are the integers that came from my avoiding set in the integers, capital A, and the deltas are between 0 and 1. 0 to 1 over n, I'm sorry. Yeah. Okay. All right. So let's see. We might end up looking at, in fact, can I do the following? Let's try instead. You will see in a minute why. But I'll So instead of 1 over n, we can also choose, let's say, a fraction of it. Let's say 1 over, instead of 1 over n. You will see in a minute why I might need to shorten this interval little bit. Let's say 1 over 3n or something. But it won't, you will see why. You don't have to believe me right now, but let's keep going. So I'll keep it as a 3n right here so that you will see later why that comes in. Okay. So let's keep going. So what does it mean to say if x plus z is equal to 2y, so this is my AP condition, if this holds, this implies that if we just plug in a sub x plus a sub y minus, sorry, a sub x plus a sub z minus 2a sub y divided by capital N plus delta sub x plus delta sub y minus delta sub 2 delta sub y is equal to 0. Okay, so let's try simplifying a bit more. So multiplying throughout by capital N is equal to 0. So let's see where we get from here. Now, how large can this object possibly be? This in absolute value is less than what? Each one of these, remember, was between 0 to 1 over n. Let's forget the 3 for now. So this would be less than 2 over 3n. Okay, so this is because of this property. So this is less than 2/3. Okay. On the other hand, if this is non-zero, then it has to be at least bigger than 1 in absolute value because these are integers. So that's a contradiction, which means that this object must be 0 as well. So that means, so this is a contradiction. That means ax plus az must be equal to twice ay. In other words, the integers a form an AP, but they came from an AP-free set. What does that mean? That means that a sub x, so it must be the trivial AP, must be equal to a sub y, must be equal to a sub z, which meant exactly as you said, that x, y, z lie in the same basic interval of E1. Great. Now iterate this argument. To show that x, y, z lie in the same basic interval of En for every n, which means that the diameter of the set XYZ is less than or equal to 1 over capital N to the n, which goes to 0 as n goes to infinity, which ultimately implies that the only possible AP is the trivial one. Okay, so that's the AP free part. Let's go back to the other piece, which was to show that the Minkowski dimension of E is 1. And let's remind ourselves what the Minkowski dimension is. We have to cover the set E by a sequence, by a collection of intervals of certain length, and then count how many such intervals there are, and show that that's close to arbitrarily close to 1. Okay, so that's our goal. Any thoughts? What should we choose as our covering intervals?
I mean, I would want to use those thickening, and I think
Yes.
we did some lower bounding above. I would feel like that might
Okay.
be useful.
Okay. So E is contained inside E sub n, right? And how many let's go back and take a look at what E sub n is. So maybe this is a good time for us to write down here what E sub n looks like. So remember that this has a very special type of expression, A1 over n plus A2 over n square plus a little n over capital N to the little n, and these are the thickenings. And each AJ belongs to that avoiding set. Okay, so I want to use these as the covers. So what is delta? What delta are the sort of the size of the interval. So what is delta in this case?
1 by capital N to the small.
Very good. Capital N to the little n. Okay, great. And how many intervals do we need? So this is the number of intervals required to cover E. So we need exactly as many choices of A1, A2, AN there are. How many such choices are there?
Sorry, what was A sub N exactly again?
This capital
Yeah,
A sub
the capital one. Yeah, capital A sub N.
n? Right. So remember, capital A sub n was my avoiding set in the integers. This was my first step. My first step was to create an avoiding set in the integers, and this capital A sub n was this AP free set that came from step 1.
Did we say how big it was?
Well, here we didn't, but of course in step 1, from step 1, we have some idea how large it is. So we have to go back to that. So for
Right.
the moment, let's just say that we'll of course go back to step 1 for the actual size. That's where the size has been stated. But for now, if we just say that it's the cardinality of capital AN, do we know how large that is? So just in terms of cardinality of capital AN, what is the size of delta n delta of E?
This is cardinality of capital A and to the N, to the small
That's
N.
right. That's right. Okay. Great. So, with that in mind, now let's do our Minkowski dimension calculation. Remember, for the Minkowski dimension, we need to look at the log of n delta sub of E divided by log of 1 over delta. So this is going to be the cardinality of an with a log, the n comes out, divided by log of capital N, the n comes out, and this is log of cardinality of a sub n divided by log of. Okay, great. So now our goal is to show that this is arbitrarily close to 1. Okay, so let's go back and see if we have that from our Behrens construction or Salomon-Spencer's construction. So let's scroll all the way back, and this is where we chose the set. So remember, capital N for us was b to the k, and k could be arbitrarily large, and cardinality of this an, the AP free set, was b over 3 to the power of k minus 2 divided by k. These were the two choices that we made, and now let's go back and see where that leads us. Hopefully it will get us somewhere close to 1. So here we go, continuing. This is from step 1. So this is the log of b over 3 to the power of k minus 2 divided by k, divided by log of b to the k. And what does this give me? K minus 2 log b minus log 3 minus log k divided by k log b. Okay, and let's take a moment to see that this is, which is arbitrarily close to 1. For k and b sufficiently large. Okay, so I'm going to stop here. We'll have, let's do a round of questions for related to the lecture first. And then if you have other academic questions, I'll take those questions as well.
Hello. I had
Yes,
first of all, it was a really interesting lecture. Thank you. Uh, I just wanted to ask something that is not really. It's only sort of related to the lecture. It's about Minkowski dimension. I
yes.
understood what we did here towards the end, but I didn't quite get the intuition behind Minkowski dimension. So is it possible if we could just do like an example related to it. I think it was earlier mentioned that, for example, the set of reciprocals of natural numbers has got Minkowski dimension half or something like that. I might be wrong. So if we have the time for it, would that be possible if it's a quick definition?
Yes, of course. So let me make sure I understood your question. So you wanted some intuition on what it is that Minkowski dimension is trying to capture. Did I get that right?
Yes, ma'am.
Okay, great. So let's try writing something out. Okay. So what is Minkowski dimension? So the like Hausdorff dimension, Minkowski dimension is a measure of size. Okay. Is and the is very important. It's one among many measures of size. Okay. If it takes roughly delta to the power of minus alpha many delta balls, and by this I mean in the real line it's intervals of length delta. In R. If it takes that many intervals to cover E, then the dimension, the Minkowski dimension of E is alpha. That's really what it boils down to. As alpha gets bigger and bigger, um, you need more and more delta balls to cover it, and alpha has to get larger and larger. So, for example, if you think of, let's say, um, how do we do this? So let's say, for example, 1, if we look at all the rationals in 0, 1, let's say, okay? So this has Minkowski dimension 1. Why? Because if you, no matter how small of a delta you pick inside your interval 0 to 1, there will be rationals in all of them. So you need every single interval to cover the rationals, and then the only possibility is for alpha equals 1. On the other hand, if you, let's say, choose the Cantor middle third set, okay. So what does this do? In the Cantor middle third set, you start with 0, 1. You look at the middle one third of the interval, 1/3 to 2/3. You throw it out and you just retain um, just the two edges. And then you repeat the construction at the next level. You throw out the middle one third of each piece and you keep just the two edges. Okay, so that's how it goes. In general, at the nth iteration, 2 to the n intervals, each of length 3 to the minus n. So you require 2 to the n many delta balls. So delta is 3 to the minus n, and the number of delta balls that you need is 2 to the n. So if you write this down, this is going to end up becoming log of 2 to the n divided by log of 3 to the n as n goes to infinity. So this is log 2 over log 3. Does this give you an idea about how to calculate it?
Yes, ma'am. Thank you so much.
Okay, great.
So I had a very vague question that just came into my head.
Yes.
So at least when dimension is integral, sort of, yeah, when the dimension of some set is integral, it's one could perhaps think of it as specifying how many pieces of information one needs uh, to specify a member of that set. Kind
Yes.
of. Is there an interpretation like that we can give to these fractional dimensions, but say the Minkowski or the Hausdorff dimension?
Okay, so let me make sure I understood the question. For integral dimension, what did you say was the intuition?
One way to think of it is perhaps I can specify a point in a two-dimensional set with two pieces of information.
Oh,
Uh,
I see.
yeah,
Um, okay, so you are thinking, so perhaps I think what you are thinking about is the notion of dimension from like in differential geometry. So if let's say you are thinking if you have a set that is two-dimensional, then you need two parameters to define it. That's what you are thinking. Is that so that it has 2 degrees of freedom?
yeah.
Okay. The answer in the fractal geometry case is that there is that intuition is no longer true. Simply, in fact, it's intentional. You see, when you talk about, let's say, a two plane in R3, you are thinking of expressing that plane using two parameters x and y, and that implicitly assumes a degree of smoothness of that surface or that plane that you are trying to study. In fractal geometry, that smoothness is absent. In fact, that is what makes the study of these fractals non trivial. Because we lose that smoothness, that parametrization, which is actually a marker of the signal of that smoothness, is thrown away as well. So if you, there is no way to um, say that we will, we have a way of, there is an alpha dimensional parameter. Typically, this is not true. There may be special cases where it may be true. For example, let me show you an example where you might, that intuition may work, but this is definitely not the case in general. So let's draw a picture. So we just now talked about the Cantor middle third set in R as being having dimension log 2 over log 3. Now suppose we look at the plane and a circle on the plane. Okay, and let's say we choose a Cantor set on it. So this one, let's say, will be left out, and we will pick this one, and maybe let's say do a little bit more. So like a Cantor middle third set over here. Okay. Then we do the same thing again, and we can pick a so a Cantor middle third set on the circle. You could parameterize it by e to the I theta, where theta belongs to the Cantor middle third set in the real line. Okay, and this parameterization is alpha dimensional, with
Right.
alpha being log 2 over log 3. So this is one way of using the kind of parameterization you were describing to create fractal sets in higher dimensional spaces. But if you go back to the original example that it came from, for example, this one, the one in the real line in 0 to 1, I at least don't know of any parameterization like the one that you are thinking of to bring to bear on this case. Of course, we can use this and use this to parameterize other sets. That's completely fine.
Okay. I I think that makes some sense. Yeah. Thank you. Thank you.
Okay, you're welcome.
Malabika, hi. I have a small question. So
Yes.
you have attributed this construction to Salem and Spencer and Perrin. So I mean, these two articles, these two different constructions, were they giving us same set, or I mean, there were some minor differences between them?
No, they were both the same set. I think perhaps the paper that I have always looked at is the one by Salem and Spencer. Berend's paper, I believe, is in German, so kind of out of my reach. But however, the the
Okay,
the lower bound is the same. So let me see. The whole point of this is that the AP free set, the cardinality of this AP free set in the integers A, if A is a subset of Z mod n, this is going to be larger than e to the power of minus some constant times the square root of log n um, times n. So this comes out from both of their work. But using spheres and like using a geometric property and translating it to the integers to create an AP free set, it occurs in both Salem and Spencer as well as in Barrett.
right. Okay, thank you.
Okay.
Okay, thanks a lot, Malabika. And
Okay.
yeah, thank you very much. Good
All
night.
right.
Very
So
nice.
I'll see you tomorrow then. Same
Yes,
place, same time.
yes, yes, exactly. Thank you.
Bye.
Thanks a lot. This is a very interesting construction. Thank you.
Thank you. See you tomorrow. Bye now.